I probably should hit OK on that. And then just put this in the corner. All right.
Okay. And now, all right. I think we have. Yeah. Yes. Yes. Okay.
All right.
Let me just get my own notes. Okay. All right, everyone. All right. Thanks everyone for coming. This is the first PhySU the third PhySU undergraduate colloquium this year and in general ever. I would like to welcome this week's speaker, Akash, who is studying mathematics and chemical physics.
Yep.
And I guess he will tell us today about spectroscopy.
I will.
Yep. Thank you.
All right. Hello, everyone. As you might have guessed from the title, this is a talk about spectroscopy, in particular, as applied to molecules and atoms, which is a little bit more of what like a chemist would be interested in, and then maybe what a physicist might look at. But there's lots of physics to be found here too. That's really why I wanted to bring it here, to show what physical chemistry and chemical physics really has to offer. So if I can move on to the next slide, then, I mean, if you were to give spectroscopy in one sentence, you'd say, oh, it's the interaction between matter and light. Whether you're treating it as classical electromagnetic waves or as photons, it's a very broad category with a lot of applications. But in particular, what I want to focus on today is these emissions and absorptions of light. So typically, the archetypical model is you have two quantum states, and you have emission of light when it drops from a higher energy state to lower energy state, and absorption of light to get from a lower energy state to a higher energy state. That is a lot of what is of interest in both like atomic and molecular systems, but you can also do more scattering experiments, things like that. But a lot of the ideas you'll see here actually will apply more generally to that. And so, admittedly, okay, atoms throwing photons out and absorbing photons doesn't actually sound the most interesting topic in the world, right? It's not the most esoteric or super crazy physics thing. But I would like to argue that it's worth looking at for a couple of reasons. I mean, one, more on why it's actually useful is that quantum mechanics is essentially founded, primarily, one of the reasons it's founded was to understand hydrogen's absorption and emission spectra, which is exactly what we're going to be looking at today. And this question of, okay, how are we getting these discrete levels when we should expect a continuum was exactly what motivated the founders of quantum mechanics when they were studying it and developing things like the Schrodinger equation. So in some sense, like, this spectroscopy is kind of our best way to probe what's going on at the atomic level. But even more, at more of a higher level, it's not as simple as just, okay, let's just throw a bunch of electrons in, let them absorb light, emit light. Because if you consider this, for example, these are two complexes. One has a chromium-based complex, one's a manganese-based complex. Manganese has essentially one more electron than chromium. So you might expect, okay, well, one more electron should mean it's going to absorb and emit light even better, and hence it should be more intensely colored. But clearly, that's almost colorless, and this is a much brighter blue. So this must be something more to spectroscopy than just photon goes in, energy goes up. And even if you aren't as interested in atomic molecular systems, spectroscopy is used far beyond that. If you're, for example, studying astronomy, really the only way you're going to be able to access stuff from so far away is through light emission and the EM waves you're able to receive here on Earth. So for example, if you're studying the composition of interstellar clouds, you might take a look at its IR spectrum and look at the kinds of peaks you see and use that to essentially fingerprint what molecules and atoms you're going to find in there. But more generally, even beyond just the actual applications, I think spectroscopy is a very interesting problem because it's not something you can solve exactly, right? The most popular physics meme about quantum mechanics, maybe besides Schrodinger's cat, is, we can't solve helium. All we can do is hydrogen-like atoms. But if we want to look at, say, like Buckminster fullerene, which has 360 electrons, that's not a hydrogen atom anymore. So we can't just do SPDF orbitals and say it's close enough to hydrogen to call it a day. We can't solve this exactly. So the big question we have to figure out is, how can you analyze such a system without being able to solve it exactly, and yet you still want to figure out some meaningful statements about what happens to these things. So I think the way you approach this problem is kind of valuable to study just more generally. Is when you can't solve something exactly, it doesn't mean that there's nothing you can say about this kind of system. What we'll see is that while you can't track the exact dynamics, you can still say a lot about, well, can I do this thing? Can I not do this thing? And you can make much broader statements like that. And so it's still something you can study if you figure out the right tools to address the problem. So, of course, this is a quantum mechanical problem. So just to kind of quickly summarize quantum mechanics and also make sure we're on the same page in notation here, I'd like to go through in brief the important ideas we need to have here. So quantum states are just elements of some complex vector space. So if you're familiar with Rn or Cn or even just 3D space, you can add them, you can multiply them by scalars. That's their kind of way, that's their additive, and that's essentially the structure of how they exist. You can also view them as a wave function, which there's a nice correspondence you can develop between that, and we're going to kind of move pretty loosely back and forth between them. And the wave function is nice because it gives you a nice interpretation of probability densities, which is especially, you might think, is important if you're looking at some extended molecular system. You want to know where is an electron actually located. You'd want a wave function is a more useful idea in that case than some abstract vector because you actually have spatial information there. Very critical to what we're doing is that the notion of an inner product on this vector space, which is going to let you essentially find all the probabilities we're looking for. And very interestingly, it takes on a form of an integral in when you go to 3D space and you consider wave functions. And that integration is actually going to be very key in a lot of what we do, because you've integrated before. You know that if you integrate an odd function over, say, over a uniform domain, it'll be 0. So maybe that kind of idea will crop up again and again that, well, maybe if we had some analogy to being an odd function, we could say, that integral is 0. And that might actually give us new information about what's going on. Since we're looking at emissions of light and absorptions of light, we're essentially asking, if I start in this first state, what's the probability I go to the second state and emit a photon to get there, or probability I absorb a photon and go to the second state? So it's important to understand what these probabilities actually are. And the way you do that is for each observable quantity, you can take a self-adjoint operator associated with that quantity. You can self-adjoint it emits an eigenbasis, and you can hence expand your wave functions on that eigenbasis. And then you take those expansion coefficients, those essentially give you probabilities. So really, for us, our question is, if I start with a state in one place, how are those expansion coefficients going to change with time? Because if we can understand how those change in time, that will tell us essentially, is there a transition occurring? Is there not? Is it a strong transition, a weak transition, and so on? And so, of course, for that, we need a dynamical model. So the dynamics is encoded through the Hamiltonian. It just says the temporal derivative of the state is given by, essentially, it's proportional to the Hamiltonian acting on the state. And that's actually a very interesting idea, because initially it did seem like we're going to have to treat this as a twofold problem, right? We need to understand what states are there, and then we need to talk about how do we move between them, because you can't talk about transitions unless you know what states there are in the first place. But because the Hamiltonian both encodes the energy states of the system and encodes dynamics, it's actually a purely structural problem. Once we understand the structure, we can already say a lot about the dynamics. And so just to kind of illustrate that, I wanted to consider just like a general model for a semi-classical absorption or emission, where essentially you have some starting unperturbed Hamiltonian like H naught, so say like an atom or a molecule. To that you add an external electric field representing like the incoming radiation, and from studying electromagnetism, you know that a dipole would interact with an electric field via essentially dotting E with mu. And so what we find actually in quantum mechanics is that the most prominent transitions tend to be these dipole-oriented transitions, where the dipole operator for the atom, or the molecule, which is essentially given by summing over charges and their positions, that will induce the bulk of the transitions. And so for the purposes of today, that's what we're going to look at primarily. We're treating the EM waves fully just as a classical thing, no second quantization photon fields for today. But because a lot of the ideas can still be understood just through this little simpler model. And so this is kind of the picture we're looking at, right? So you take psi I and psi f, initial and final states. They're eigenstates of the unperturbed Hamiltonian. So say your pure atomic Hamiltonian or pure molecular Hamiltonian, and you're interested in, say, an emission that releases light, and that all those transitions are induced by this E dot mu term. And so the important idea is that because we have this from the Hamiltonian, all the transition strengths are determined by this matrix element of mu within H. And that just kind of comes from, if you say we were looking essentially at some time t, we have a coefficient on the initial state plus a coefficient on the final state. And we want to see how is this going to decrease, and then this quantity grows out of zero. Because initially, we just start with everything primed in the initial state, and then it allows some transition probability into the final state. But we know how to get this, how this coefficient changes in time, because it's obtained from the Schrodinger equation. Essentially, we can just dot or take the inner product of the final state with just the time derivative of your overall state to get the to get how this changes. But because this is proportional just to the Hamiltonian by the Schrodinger acting on the state by the Schrodinger equation, you can probably do that. You can get this. But this term, this H naught term, can't couple anything because psi I and psi f are eigenstates of the Hamiltonian. So this actually is just proportional to psi f mu psi I. And so this quantity here is essentially what we're going to spend the rest of this talk looking at and trying to understand. Because if you can understand this, if you know, for example, this is 0, then this CF is going to remain 0 for all time. It's not going to you're not going to have any transitions from here to here. But if it's non-zero and maybe strong, very, very large quantity, you could get a very fast transition between the states. And so, but this is a purely structural idea that if we understand the states and we understand what these matrix elements look like, then we know the dynamics. And so just to kind of show this is a non-trivial observation, I wanted to consider like the hydrogen atom, which is something we actually know how to solve. So the hydrogen atom states are, they're indexed by NLM. N is just energy, L is really the total angular momentum, and M, which is the quantity we're going to look at for today, is the Z component of the angular momentum. It's some polynomial times a spherical harmonic, but if you just put all the theta terms and R terms together, you're left with some function times and a complex exponential. So we want to evaluate, and also for our system, it's just a single atom with a single electron. Mu is just the position operator for that electron. So we want to evaluate this matrix element, MZ, for example. So the Z component of this dipole operator between the states. And so if we go to wave function representation, it's just this integral over the final state, complex conjugated, times Z times the initial state. And I realized that front term actually should be unprimed indices. But so when you do that and you find that out, using the functional form of this, that this is just some function of R and theta times a complex exponential, you get this, do this integral of spherical coordinates, and then you notice that the phi term is just this integral of a complex exponential from 0 to pi. But you know that that is just proportional to a Kronecker delta, as in m has to equal to m prime, or else this thing is 0. So what we actually immediately find is that this matrix element can only be non-zero if the initial z-component momentum and the final z-component momentum, those quantum numbers, are the same. And so you can do a similar thing for the x and the y components of the momentum of the dipole operator. And so with x, you get a cosine phi term that turns into e to the I phi plus e to the minus I phi over 2. And so you'll get, instead of they have to, m and m prime to be the same, they have to be adjacent by each other by 1. So that's what that Kronecker curve essentially says. And similar for my, you get a sine of phi, and that's what you get. So yeah, essentially it's because there's a few ways to look at it. One is that, like, for a hydrogen atom, like it kind of literally is a dipole. If you take it's a positive charge and negative charge, so that is more of a literal dipole. If you consider a more general charge distribution, generally you can take like a multipole expansion, which has a dipole term, a quadrupole term, and so on. And you generally experimentally find that the dipole term is what dominates. So today we're kind of just focusing on the dipole interactions, but in general, a lot of the same principles will actually apply for like quadrupole transitions, magnetic dipole transitions, and so on. So focusing on this actually isn't losing too much generality. But so what we have is that this matrix element, for if you take the z component of this mu operator, because it's really three operators in one, encoded in a vector operator, m has to equal m prime for there to be a non-zero matrix element. But for my and mx, it has to be plus minus 1 of each other. And so that actually gives us our first example of a selection rule, where if we're looking, say, at where we have to have delta m is 0 for an mz transition, and delta m is plus minus 1 for mx or my transition. And that in itself is already a pretty powerful statement, because without having to solve for the explicit dynamics, we already know that certain transitions cannot happen, and certain things are forbidden from occurring. And so this idea of a selection rule is kind of how we attack a lot of spectroscopic problems, because since we can't solve the exact dynamics, maybe we can look for what's forbidden, and at least say this thing can't happen, or maybe this thing can happen, and attempt to understand it that way. So another kind of immediate example you can see is that the Hamiltonian we looked at in the last slide was spinless. It didn't have any spin, didn't act on the spin component. So if you assume there's no spin degrees of freedom, which is an approximation that ignores like spin over coupling, things like that, then you get that, well, the total spin can't change through that process. And so that actually is immediately useful, because if you look at that system we had before, where we were a little perplexing why adding electron actually gets rid of any transitions, what happens is that if you look at the allowed states of this manganese complex versus this chromium complex, the manganese one doesn't have any transitions that are so-called spin allowed, where you can, the initial state and the final state have the same spin values, whereas the chromium complex does. And essentially it's because you threw in the electron that you kind of lock out that possibility. And so, but then you can keep on probing this problem, because let's say you added on, instead of these water molecules essentially binding to your manganese, if you added oxygen atoms instead, which are they essentially tightly bind onto it and form a coordination complex, you get this very strongly pink permanganate solution. And so that indicates that whatever's going on in here, there's something in there that will allow you to bypass that old problem of not having spin allowed transitions. So what turns out to happen is you essentially have transitions from the oxygen to the manganese. You can have these they're called like ligand metal charge transfers. And so that, just probing things spectroscopically and looking at what colors you see, or whether you see colors or not, that allows you to say that there's a qualitative difference in the electronic structures of these different species. So that's already, and that just kind of came out of taking a matrix element and saying it has to be non-zero to have anything useful. But obviously we kind of got lucky there, right? We just said, let's try taking this matrix element, see if we get anything, and we got something nice. We have to ask, okay, how do we do this more generally? Is there a way to do it systematically? And more importantly, we can't just calculate these matrix elements explicitly anymore, because with hydrogen we had analytical expressions, but once we get to anything more complex, we won't have anything analytical anymore. And another issue is, we kind of did it in a basis-dependent way because we rely on the fact that we use hydrogenic orbitals, which we typically label by angular momentum. So one could ask is, let's say I knew the states of a quantum system and I attempted to find these transition rules. Maybe I don't find anything, but that's just because I picked the wrong quantum numbers to work with. But maybe I can change my basis and find something that does work. And so we're going to have to figure out, is there a better way to do this that doesn't just involve trying to calculate as many integrals as we can? And to do that, I'd like to return a bit to the hydrogen atom. Because there's something kind of funny about the fact that mz conserves momentum. It conserves the z component angular momentum, but mx and my do not, right? Because the fact that mz transitions would be like, say you have an incident electric field coming in up the z direction, like this. And so delta m equaling 0 just says that the z component angular momentum, which is m, is conserved in time. Because if you start in this initial state with this value m, you'll have that for all time. Or more generally, if you started in some superposition, you would keep that same that expectation value the same. It would remain the same for all time. And it's kind of funny that that coincides with being rotationally symmetric about the z-axis. Whereas these transitions we had delta m being plus minus 1, for example, are when you have an electric field incident from the x-axis, and m is no longer conserved. But that also coincides with not being rotationally symmetric about the z-axis. And so if this were classical mechanics, you'd say, well, that's just Noether's theorem. That's just expressing the relationship between rotational symmetry and conservation laws. That Noether's theorem says that, hey, if you're rotationally symmetric about the z-axis, then the z component angular momentum will be conserved. But we're kind of seeing something similar in quantum mechanics here. And it turns out that there is essentially a quantum analog of Noether's theorem that relates continuous symmetries and conservation laws. So in our case, the LZ component, so the z component angular momentum, this operator generates rotations about the z-axis. So the idea is you take your wave function, and then you just rotate it by some angle about the z-axis, you get a new wave function. To do the operation that takes you from here to here is obtained by exponentiating the z component angular momentum times whatever angle you want to go by. But since our Hamiltonian is invariant under these rotations, because on the previous slide, if we consider the left-hand side, if you rotate the electron, it's going to clearly be the same system because there's nothing differentiating it being here from it being here, since the field's just coming up from below. So H is actually invariant under these rotations. And that means that we can, if we consider a really tiny rotation, then e to the ILZ theta for a very small theta is to first order in a Taylor expansion 1 plus I theta LZ, basically. And so what you then get is, well, if it's invariant or infinitesimal rotations, then the commutator H and LZ is actually 0. That's essentially the quantum analog of classical conservation laws, classical symmetries. But we know from linear algebra that if two operators commute, then the eigenspaces of one are invariant under the action of the other. Right? Because if you just have, say, two operators A and B, and we know that AB equals BA, then if we have a vector V such that B V is some lambda V, then if we consider what happens when we map A to it, and we apply B to that, we can just swap these two and get ABV, which is just lambda AV by linearity. So mapping an eigenspace just gives back something in the same eigenspace again. But that's essentially what we saw earlier, because the fact that mu z, the fact that if you tried to apply H, essentially, so our mu operator is part of H. If we try to apply that to a state of definite angular momentum, like we did, we found that the only way to have non-zero matrix elements was that if you had the same angular momentum. But that's just a statement of the eigenspaces being stable under the action of H. So conservation laws can take on this new form via commutation relations. And so we're seeing an example of that with the hydrogen atom. So maybe this is telling us that we can use symmetries to understand spectroscopy. And so let's try that. There's only one problem, though, which is you take a molecule, say like this boron trifluoride, it's essentially this planar system with a boron in the middle and then three fluorine atoms sticking out. That doesn't really have any continuous symmetries, right? If you rotate it a little bit, it's going to change because because the fluorines aren't like a continuum. There's just 3 of them. But intuitively, you'd say, well, there are definitely discrete symmetries. If you rotate this thing 120 degrees, if you reflect it across the axis, for example, or reflect it down the axis of the fluorine, you get the same thing back. So intuitively, you have these discrete symmetries, like rotating about 120 degrees and rotating about the fluorine axis, rotations, reflections in the plane, across the plane, and so on. But if you compose 2 symmetry operations, if you do 2 things, if each thing just preserves the molecule, then so will composition. So this is just a group. This is which, there's a sensible notion of composition via just applying 2 symmetry operations. So we actually have a group structure for the symmetries of a molecular system, and these are called point groups. So for example, for our boron trifluoride molecule here, we have that it's in a D3H point group, which just says E is the identity, and then we have these different classes of rotations about the different axes shown, and then the sigmas signify reflections. So you have reflections in the plane, and reflections kind of cutting through the plane of your central axis rotation. And then those S's are just what happens if you compose a rotation with a reflection, because you want it to be grouped, so you need everything. You need compositions to remain within the group. So for completeness, you have to include these rotation reflections. But that's actually quite a powerful observation. And just as an aside, if you want to go through classifying every molecule via its symmetries, there are these giant flowcharts you can use. But for the purposes of our discussion today, we can take the pure mathematician route and say there exists a symmetry group and just be happy with that. But the fact that we have a symmetry is actually quite useful, because we can then consider that these symmetries have natural operations, like natural operations associated with them. They're not just abstract elements of group. You can also consider how they act on like a physical rotation as a matrix, for example. So if you consider like a classical configuration space with just atoms sitting in our atoms sitting in R3, for example, or you consider a quantum state space, they're both vector spaces. And these symmetry operations, because they're naturally geometric, have natural interpretations as linear operators. So for example, that rotation of the wave function we saw earlier is essentially what's called a representation of rotating of the rotation matrix element or rotation group element. So if we take all of our group elements and just make them into matrices, kind of be the natural way of what we associate with a rotation or a reflection and things like that, we get what's called a representation of the point group. And so for example, if we considered a reflection across the xy plane that just negates everything in everything across the z-axis, so it's the identity with a -1 at the end. Rotations about an n-fold axis means rotating about 2 pi over n. So that's kind of your usual idea of a rotation matrix. So you're rotating about the z-axis here. And then if you took a composition, which is a rotation reflection, you observe that, oh, it's just what happens is you compose both of these naturally. And so when you map these group elements onto matrices or linear operators, we preserve the group structure. And that's essentially the defining thing about representation. And so this is actually quite powerful, because we can use this as our basis of symmetry and how we're going to understand molecules going forward. So this is just notation-wise. I'm going to use pi and then a group element to represent the matrix for that group element. And then that same that pi of d1, pi of d2 equals pi of d1, d2 is just saying that whether you consider a group element as this abstract thing or as a matrix, you have the same idea of group multiplication. And that's what it means in representation. So this doesn't immediately seem that useful, because it's like, okay, we've defined a bunch of matrices for some abstract group operations. But how is this actually going to get back to our problem of understanding molecules? Is that this group and these group operations are essentially going to give us an underlying structure for our vector space and for our quantum space, for a space of classical particles. Any vector space you put this on. And that's basically irreducible representations. So these aren't entirely arbitrary matrices or operators. Because we've essentially imposed that group structure, it turns out that via an appropriate basis change, we can actually just block diagonalize all of them. And so there's a little asterisk on that, which has to do with dimensionalities. But for purposes of our talk today, we're looking mainly at finite point groups because there's only a finite amount of symmetry elements. So for what we're considering, it is true that we can always decompose them into what's known as into basically a sum of irreducible representations. And so we'll see an example on the next slide, but the important thing to keep in mind is that, so each of these blocks is called an irreducible representation or an irrep, and for finite groups, there are only finitely many of these, which suddenly means that our problem of understanding these very large infinite dimensional systems can reduce down to this finite problem of understanding just these irreducible representations. So an example is like, if you consider the C3V point group, which is roughly saying, for example, that's like what chloroform looks like. Essentially, it says you have rotations about a central axis you can have of 120 degrees, and then you also have some reflections to the planes. But that's the kind of the picture to keep in mind. It has three irreps, A1, which is the totally symmetric, A2, and so both A1 and A2 will be one-dimensional, as we'll see, and then E, which is this two-dimensional irrep. And so if you consider just C3V acting on R3 in the natural sense of like the normal idea of rotating around the z-axis, reflecting across the x-axis, y-axis, you get these matrices. And what you see is that there's clearly this block structure where the top two things are in their own block, and the bottom thing is in its own block. But what's interesting is that the bottom block is just all ones. And that's this A1 for this totally symmetric representation, which is kind of just the trivial representation of everything's identity. Nothing happens when you apply this to that third vector. And that 2x2 block was our two-dimensional E representation. And so because we kind of just defined it this way in R3, these are manifestly in this block diagonal form. But in general, even if the matrices don't look diagonalized at first, you can find a way to diagonalize them after. It's just you won't be in your initial basis, you'll be in this new like symmetry adapted basis, which actually turns out to be quite useful for us because somehow through our choice of basis, it's almost like the Hamiltonian can kind of sense that, or it's built into the Hamiltonian, the symmetry-based basis. Because one can actually check that the Hamiltonian is block diagonalized by these symmetry labels. So basically, if H is invariant under these operations, so basically for our case, that'd say, oh, we pick the appropriate if we pick the appropriate point group, then the Hamiltonian will be invariant under those operations, because that's kind of why I pick the symmetry, is that if I rotate, for example, that boron trifluoride by 120 degrees, I get the same thing back. So the Hamiltonian will do the same thing if you rotated it, then apply the Hamiltonian, or if you just apply the Hamiltonian, then rotate it. So that's just our expression of symmetry. Then H will block diagonalize into just these blocks are labeled by the irreducible representations. And that's pretty interesting because anytime you can block diagonalize a matrix, basically means you just reduce the problem down into studying the individual blocks. In particular, if you wanted to consider what the eigenvectors of the Hamiltonian look like, it's just you can just solve each of them individually, which means that all of your eigenstates are also contained essentially within this irreducible representation. And that means we can label the energy states of our system without ever solving for them explicitly, which is going to turn out to be very useful. Because the other half of this story is that if we consider a space of functions, say of wave functions, and they belong to this irrep. So for example, if you consider the first vector in that block is like an A1 vector because everything acts on it like the A1 irreducible representation, which is just the trivial thing. Then the integral of a function belonging to the integral of a function will just be 0 unless the function has a component belonging to that A1 totally symmetric block. And that looks almost like a selection rule because we were originally considering ray functions and what lets their integrals are non-zero, and so we're going to have to do that again here.
What do you mean by selection?
Remember earlier we had that MZ. We were integrating to see if that matrix element was 0 or not. Yeah. That is essentially what we find here is that most things are going to integrate to 0 unless they have a certain symmetry. And that's essentially the idea of a selection rule. It's kind of classifying when these integrals are 0, when they're non-zero, and so on. And so just to give an idea of how this actually works out, I want to consider the octochlorodiamolybdenate anion, which is quite exotic, having a quadruple bond, not something you see every day. So this has a D4H symmetry, which basically means that you can consider 90-degree rotations about that center MO axis. And you can also consider, for example, reflections across the central plane. It'll look the same whether you reflect it or not. And just the wedge bonds, like the solid wedges mean into the plane, out of the plane, and the wedge bonds mean like back behind the plane. So you essentially have like this kind of looking thing, where this kind of goes out. And so that's kind of the skeletal structure of what we're looking at. So one kind of transition you're often interested in is the transition between the so-called HOMO and the LUMO. The HOMO is the idea of a highest occupied orbital, and the LUMO is this lowest unoccupied orbital. And so often, because we know that our eigenstates are going to be labeled by the point groups, and are going to be labeled by the EREFs of our system. So, for example, what you can there's a way to kind of qualitatively construct a good guess at what this highest occupied molecular orbital, this lowest unoccupied molecular orbital will be, based on this idea that we have to respect that symmetry. And so each of these looks pretty symmetric, and it turns out you can classify them by what EREF representation they belong to, as we would have expected by the fact that H block diagonalizes. So the way you usually do this by hand is you essentially have a table called the character table that gives you the traces of each of the irreducible representations. And so, for example, that A1 totally symmetric thing that was just the identity everywhere, you basically get this row you have this A1 row that's just 1, 1, 1, 1, 1, because everything is just a 1 by 1 matrix. And so by inspection, we can actually pretty quickly classify what EREFs these belong to. Because so in the bottom left, we have the character table for the system. And so just kind of by inspection, you can check that the HOMO is in the B1G EREF. So for example, if you reflect it across the plane, nothing happens because it's symmetric about that reflection. So if you look at the B1G row and you look at that sigma H, you'll see a 1 for the B1G row. And that just says that the trace of the sigma H matrix acting on a B1G EREF will be 1. But that just says, since it's a one-dimensional representation, just says that it's the identity. So that's exactly what we see here, is that whether you reflect the wave function or not, you get the same thing. On the other hand, if you consider this, you have essentially this negative overlaying this positive, right? So if you reflect this across, instead of having, you essentially get this up here and this down here. So that just says that everything's getting negated. The function is being negated. So that would just be a -1 as the matrix form of sigma H acting on there. And indeed, that's what you see when you look at the B2U EREF, and you see that it's -1 in the sigma H. So if you'd like, you can go at it and take your favorite molecule, take some orbitals and say, let me try to classify what EREF this belongs to. But for our purposes, we found it's B1G and it's B2U, and you can go through and check that if you wish. So now we want to say, hey, can we induce the transition of electron from this orbital to this orbital? Again, using that E dot mu term to induce those transitions. So as before, we're trying to we want to consider those transition integrals, right? So just to recall, these transition intervals generally would look like some final state starred with xi, which is xyz, times your initial state. And then you'd want to check, does this equal 0? Or, because if it's 0, then that transition can't happen. If it's non-zero, that transition can happen. So we're trying to evaluate whether this integral is 0. But we know that if we have an integral of a function, then because those symmetry labeled vectors form a basis, we can always write it as this sum of the symmetry labeled vectors. Let's call them GI. And then what one can check is then this integral will always be 0 unless one of these GI belongs to A1, that totally symmetric thing. So essentially our question is, if we decompose this into this basis, will there be an A1 component? And that's the question we're trying to ask, because if not, we can already say this transition is forbidden. And so, fortunately though, all of our, we're getting a product of 3 functions, right? That homo psi h, the lumo psi l, and then this xi. Each of them is already a very symmetric thing because we knew our Hamiltonian, the eigenstates would respect the symmetry. Xi, you can also check, has some symmetry of its own, which isn't too surprising given it's just asking what's the z value. So if you reflect across the z-axis, the z value gets negated. So it's not too hard to expect that there's going to be a symmetry group to it as well. And so generally, there's a good thing about this, which is that when you take a product of these symmetry labeled functions, these products are very well understood, because this in general is another function, which can then be decomposed into our basis. That function itself will not generally have a distinct symmetry, but you can always decompose it into stuff that does. So for our case, let's just consider the z transition. We have psi l star z psi h. Then psi l, we found in the previous slide, had this B1G symmetry. Psi h we found had a B2U symmetry, and then you can go work through the character table and check that z has an A2U symmetry. But actually in this case, we can actually just check by inspection that this is itself is actually behave like an A1G function, which you can kind of see just from the fact that like U and U essentially has to do with, for example, how you behave under an inversion. So U says you'll get negated if you invert the thing about some center point, and G says you're not negated. So if both Z and psi h are getting negated, since one's A2U and the other is B2U, then if you negate their product, if you put their product to the inversion, then nothing happens. So you can work through the details and actually check that this behaves like an A1G function, or you can just check a character table or a direct product table, which will include all this information tabulated for you. You don't have to do that. But since this is A1G, this says that this integral could be non-zero, which says that the transition from that homo to lumo is allowed if we have an electric field incident from the z-axis, so along that molybdenum bond. On the other hand, if you wanted to look at these psi l x psi h and then psi l y psi h to consider y and z transitions, you can work the details essentially using a table or decomposing it by hand, and you'll see that they actually don't include this totally symmetric here in their decomposition. So what that tells us is that if we took this integral with, say, x, this is 0. This has to be 0. We didn't have to check, for example, we didn't need an explicit form for this or for this. We just know that by symmetry principles, this integral is 0. And so in particular, if we wanted to consider that homo-lumo transition on the previous page, that can only happen if you have light incident or EM waves incident along the z-axis. And so, one, it's cool that we can actually do this like analytically without having exact forms for the functions. And two, I think it's you could think of it the other way, right? Let's say you didn't know what something looked like, you didn't know its structure, and you wanted to try to probe out, for example, what does its homo look like, what does lumo look like? Because a lot of chemical reactivity is based on these highest lying occupied orbital, this lowest lying unoccupied orbital. Then say let's say you did a spectroscopic experiment where you first shine light along the z-axis, then along the x-axis and the y-axis. You can see where are the allowed transitions occurring, and where are you not seeing transition, and that might give you some insight into, okay, maybe this thing has this symmetry or this symmetry. And so experimentally, now that we're able to derive these selection rules just on symmetry principle alone, that actually gives us quite a powerful tool if we want to start studying things with that. And that is commonly used, for example, in inorganic chemistry when you're looking at these kinds of transition metal complexes. But I also want to kind of go back and say, it's worth thinking about what did we exactly ask for here, right? We didn't ask, give me the exact dynamics. We just said, can I tell you if this thing is allowed or not allowed via symmetry alone? And it's kind of not surprising that that's the kind of question we can ask, because that's exactly what symmetries always allow us to do, right? If you considered in classical mechanics just a particle in some potential well, and you knew it started with some given energy, even if you don't know the exact dynamics of the particle, you can always tell me that, well, I can never find it up here because that's disallowed by energy conservation. But energy conservation itself comes from a symmetry principle via Noether's theorem. So we're essentially seeing the same ideas unfold here, that while we can't always solve a system analytically, we can sometimes look for what symmetries does it have and maybe start and analyze it that way. So I think it's just nice. It's kind of nice to see that unifying theme kind of showing up for these systems. And so I just kind of wanted to wrap up by talking about maybe my favorite example of what you can do with this kind of formalism, which is when you do symmetry labeled vibrational spectroscopy. I think this is really cool because you actually apply group theory both at the classical level and then again at the quantum level. So the way this usually works is, for example, you say you have a water molecule, you want to study the water molecule. Classically, it's just these 3-point particles. Classically, you'd say, oh, the nuclei are 3-point particles with some given mass, and so they have a 9-dimensional state space described by, or they have a 9-dimensional coordinate space described by 9 generalized coordinates, say the x, y, z for each of them. Usually, we work with these displacement coordinates where we say we know the equilibrium geometry from say from experiment, or just from we expect it to look like this, for example. And then we just consider how far do you displace from that equilibrium position. So Q1 would say, how much do I move this way or that way, and so on. But saying that something is a equilibrium geometry is just saying that it's the minimum of some potential. So we can then consider Taylor expanding the classical potential these particles are moving in, and we get a quadratic form because the first derivative vanishes, so we're just left with the second derivative quadratic form with the q's and the q transpose. The potential energy is also roughly a quadratic form, which will just be some, just some matrix with a q dot on one side and q dot transpose on the other. And so overall, whether you want to look at this through Lagrangian mechanics or Newtonian mechanics, you essentially have the problem of how do I solve something that's just 2 quadratic forms? And it turns out that because T is usually a positive definite matrix, and V is also a Hermitian, just because by commuting partials, you simultaneously diagonalize both of these to get the normal modes of the vibrations. It essentially says you do a coordinate change to find the quadratic curvatures of your potential, roughly speaking. And so our goal is, hey, let's diagonalize these matrices. But we can also say, if we consider the state space, we can also put group operation. We can also consider group operations on it. So for example, you rotate about that central oxygen atom just to flip all the coordinates like that. So we also can apply our group elements now viewed as matrices again. But diagonalizing, we already know from the quantum example that diagonalizing something that we have a representation on is quite easy because it just decomposes into the irreducible representations. So even if we don't want to diagonalize it exactly, we can already at least say, well, they will obey certain symmetry properties. And so again, that's what we see here. Since T and V are also invariant under these transformations, because one's just the potential, which is symmetric, and one's the kinetic energy, which is also symmetric under these operations, because we picked our symmetries according to the atom or the molecule. They're also block diagonalized. So we can just so if we wanted to, we can just diagonalize each block separately, or we can just be satisfied by the fact that we know that whatever eigenvalues there are and whatever eigenvectors there are labeled by these irreducible representations. So even at the classical level, we're finding modes labeled by symmetries. And so what you find for water, for example, if you want to solve this exactly, you'll have a symmetric stretch where they just both go where basically both the oxygen hydrogen bonds just both extend kind of uniformly. But that is A1, because if you were, say, to reflect it or rotate it, the displacement vector remains the same, because the displacement vector will say, I'll go this much in this direction, this much in that direction, which is unaffected by rotations. And antisymmetric stretches, one goes this way, one goes that way, which is clearly negated when you reflect it, because now instead of being up here and like that, you're down here and like that. So that turns out to fall under a B2 EREP, and a symmetric bend is once again A1. So one, that's cool, because if you, say, had some much larger molecule that you can't just diagonalize by hand, you can at least say, well, I know it'll have a certain symmetries to its stretches and certain symmetries to its vibrations. But if you actually want to do something with that and you want to think about the kind of vibrational spectroscopy you can do, it turns out that these symmetries, when you quantize these modes, essentially just saying each of these modes is a harmonic oscillator, the symmetries are in somewhat way they're inherited by the quantum system. And so just an example of what that means is you can consider a state where, so we're essentially treating our modes now as basically an ensemble of harmonic oscillators, right? So each of them has these discrete energy levels, and we could ask, say, well, one state is where everything is in the ground state. That is totally symmetric because the ground state of the harmonic oscillator is like this even function. So we take a bunch of products of them. That's unaffected by any kinds of symmetry operations we do. Then we consider, well, what if I raise the energy level of just one mode, say like that energy symmetric stretch mode in the middle. So we essentially are exciting that mode, leaving the other ones unchanged. It turns out that that mode, call it psi k, where the kth mode is excited up one level, everything else is the same, will inherit the classical symmetry of that mode. So this psi k has a B2 symmetry, but now viewed as a quantum mechanical vector in like a Hilbert space. So I think that's really cool because you've essentially attacked an entirely different problem of, let me solve this classical diagonalization, get normal modes. And you're actually finding that it translates into the quantum mechanical structure of your system. But then, hey, we can do our favorite thing and look at the transition moments and the selection rules now and consider what's that integral. Since psi 0 is totally symmetric, it turns out that you need psi k and xi to belong to the same irreducible representation to actually get a non-zero integral. There's essentially a theorem that says you take a product of two things belonging to irreducible representations. The only way to get a symmetric thing out of it is if they're the same representation. They belong to the same representation, the same irreducible representation. And so what we find is, well, under C2V, Z has A1 symmetry and Y is B2 symmetry. So the symmetric bend and the symmetric stretch are both allowed via some Z incident electric field, whereas this anti-symmetric stretch is actually only allowed via Y incident field. Okay. So that's kind of, I think that's a really cool application. And so I'll just leave you this, like, this is not everything, because essentially I've been using the Born-Oppenheimer approximation implicitly to talk about distinct atomic symmetries and things like that. So there's lots of ways this thing can break down. And what if you don't even have a distinct notion of molecule, like a cluster structure or a non-rigid thing? So there's lots more to think about with that, but that's a story for another day. So for now, I will thank you, and I'll say, if you want to learn more about this, these are some pretty good references on this, and these are just my photos. These are the photo references and general things like that. So Landau covers it surprisingly. Everything's in Landau, apparently. I was totally surprised. I'm like, oh, there's this whole huge chapter on molecular symmetry. Where did that, who cares? Like, why do physicists care about that? So that's everything for today.
All right. Thank you for your talk. I guess we'll switch over for a couple of questions, and then if people have to leave because we're a bit past the hour, you can also do that. Any questions? Yep. Sorry, let me just bring the microphone over to you.
Yeah. Okay. Is it picking up my voice?
Yeah.
Okay. So I'm a second year chemistry student, and I have been taking some inorganic chemistry this year. And in the course, we've been learning about forbidden transitions. And so,
Yes.
according to what you just described, those transitions shouldn't occur. So why is it that they're able to occur?
Yeah, that's essentially what I was talking about in the last slide, which is that everything I've talked about is based on this idea that we have these definite symmetries. But to talk about that, you really need an idea of a fixed molecule that has, say for our water, we know that it's going to be a hydrogen here, an oxygen here, and a hydrogen here. But of course, these nuclei themselves are also quantum mechanical, so they don't have well-defined positions. So what you really do is you use the Born-Oppenheimer approximation to talk about, for a fixed nuclear configuration, what's the electronic wave function. And that's what I've been using to say this has this symmetry. But of course, the Born-Oppenheimer approximation can break down. And that's exactly what you're seeing there with those like relaxed transition rules. But that's its own field of study and has lots of interesting consequences.
Thank you.
So
Yep. Go ahead.
So in real spectroscopy, I don't, because in reality we put a sample in a spectrometer and shine light through it. So essentially we don't care about the orientation of molecules in the sample.
Mm.
But based on what you said, it seems that there would be a difference if the light is shining with respect to molecule in X direction or in Z direction.
yeah,
There would be a difference if like the transition will occur or not.
yeah, exactly. You're right. Usually, like if you're just doing something in solvent, it's just this mess, right? But if you had a way to control the relation between that molecule and the light, then you could actually see that this way it's allowed, this way it's not allowed. I think in NMR they like spin it really fast and like that aligns some stuff, but yeah, I'm not as sure than the experimental details there.
Anybody else? Okay, let's thank our speaker once again. There are still some leftover cookies up front, so please do grab those.